Title: Competition-based Adaptive ReLU for Deep Neural Networks. Abstract: This paper introduces a new activation function called Competition-based Adaptive ReLU, CAReLU. Unlike traditional activation functions that allow positive values to pass through while blocking or suppressing negative values, CAReLU scales the input values based on the competition results between positive values and negative values. It defines two parameters to adjust the scaling strategy and can be trained uniformly with other network parameters. The effectiveness of CAReLU is verified on image classification, super resolution, and natural language processing tasks, showing better performance than other widely used activation functions. Introduction: Deep learning techniques have been evolving fast and are now widely used in various fields such as computer vision and natural language processing. A deep neural network contains thousands of neural units, each of which gathers the input signals from other neurons and generates a signal for other neurons to process. The structure of a deep neural network is a directed acyclic graph where every vertex represents a mapping from signals of incoming arcs into new signals of outgoing arcs. The nonlinear mapping, also known as the activation function, is a crucial part of this process. Without it, a deep neural network would degenerate into a linear regression model. Proposed method: The authors propose a new competition-based adaptive ReLU, CAReLU, that utilizes the competition results between positive values and negative values in the input tensor. CAReLU has two parameters that can be trained uniformly with other network parameters. Different competition indicators can cooperate with CAReLU to generate different activation functions for different tasks. The percentage of positive values energy, pay, is defined as the indicator of the competition. If pay less than 0.5, then the negative values win the competition. If pay greater than 0.5, then the positive values win the competition. By multiplying the input with the sign of the competition result when passing it to the ReLU, the input can be flipped if negative values have higher energy. However, this vanilla version of the idea does not perform well due to the discontinuity in the model's parameter space. To address this issue, the authors replace the fixed scaling factor of 2 and the bias of 1 with trainable parameters alpha and beta per layer. They also replace the sine function with the tanh function to create a smooth version of the sine function. The authors also experiment with other kinds of indicators for competition between positive values and negative values, such as the percentage of positive values L1 norm and the percentage of the number of positive values. Competition-based adaptive scaling, CAS, is defined to adaptively scale the input based on competition results. By concatenating CAS and ReLU, the authors construct competition-based adaptive ReLU, CAReLU. They also define batch normalization CAReLU, BN-CAReLU, to improve compatibility with batch normalization. Gradients of the competition-based adaptive scaling are derived from the chain rule. The authors set the initial values of alpha and beta as 0 and 1, respectively, and the constant k as 1, tanh, beta 0. Approximately equals 1.313. This makes the CAS initialized as an identity mapping when the training begins. The competition-based adaptive ReLU, CAReLU, activation function is introduced, which allows positive and negative values to compete for activation. The CAReLU has two trainable parameters that can be optimized using gradient descent. 3 different competition indicators are used to implement CAReLU: pay, place 1, and PC, resulting in CAReLUE, CAReLUL1, and CAReLUC, respectively. The gradients of CAReLU are derived using the chain rule, and the loss function is optimized using stochastic gradient descent. The method is evaluated on various applications, including CIFAR100 image classification, BSD300 image super resolution, and Stanford Natural Language Inference, SNLI. In the CIFAR100 experiment, CAReLUE and BN-CAReLUE achieve the highest accuracy among the evaluated methods, while CAReLUL1 and CAReLUC also perform well. The results suggest that energy-based implementations generally perform better than the other two implementations. The values of 10H, alpha p plus beta, in the CAReLU are evaluated, showing that the input values are scaled uniformly and fine-tuned for each sample according to the input's competition results. In the $300 Bahamian experiment, CAReLUE and CAReLUL1 outperform other activation functions in terms of PSNR. CAReLUC also performs well but is outperformed by CAReLUE and CAReLUL1 due to its discontinuity introduced by the Heaviside function. In the SNLI experiment, CAReLUE achieves the highest classification accuracy, while CAReLUL1 and CAReLUC also perform well. The results suggest that CAReLU is a promising activation function for deep learning tasks, offering a new perspective on the competition between positive and negative values. The CAReLU is also evaluated with batch normalization, BN, which provides extra performance gain. The results show that BN-CAReLU performs better than CAReLU except for CAReLUE in ResNet 18 experiments and CAReLUC in GoogleNet. The effectiveness of CAReLU makes it a promising activation function for various deep learning tasks. The paper provides a comprehensive review of various neural network architectures, activation functions, and optimization techniques used in deep learning. The authors cite numerous references from prominent researchers in the field, showcasing the evolution of neural networks from traditional convolutional neural networks, CNNs, to more advanced architectures like transformers. The authors highlight the importance of activation functions in neural networks, citing works that introduced rectified linear units, ReLU, Gaussian error linear units, GELUS, and other variants. They also discuss the role of batch normalization in accelerating deep network training. The paper references several influential papers on neural network architectures, including ImageNet classification with deep convolutional neural networks, attention-based models, and residual learning. The authors also cite works on activation functions, such as the multiphase ReLU activation function and the self-regularized non-monotonic neural activation function, MISH. Furthermore, the authors discuss optimization techniques, including stochastic optimization methods like ATOM. They also reference works on neural network visualization, loss landscape analysis, and the importance of datasets in training deep neural networks. The paper concludes by referencing various applications of deep learning, including natural language processing, image recognition, and super-resolution. The authors also highlight the significance of annotated corpora in learning natural language inference. In summary, the paper provides a comprehensive overview of the evolution of neural networks, highlighting key contributions, architectures, and techniques that have shaped the field of deep learning.